A common approach to medical image analysis on volumetric data uses deep 2D convolutional neural networks, or CNNs. This is largely attributed to the challenges imposed by the nature of the 3D data. While many of these medical image modalities are two-dimensional, computed tomography or CT scans are three-dimensional and require more computational expense in order to make predictions from the entire volume. This can be an insurmountable obstacle in the case of limited GPU memory. Complicacy also arises when dealing with the variable depth size in the data, and thus the data preparation scheme plays a vital role to build robust prediction models comprising of volumetric image data. Recent works address this problem where the 3D data is treated as a set of independent slices. These 2D slices are then used to train 2D CNNs to perform the desired prediction tasks. An advantage of this method is that it enables practitioners to easily downscale the slices to the desired shape using standard resize operations, and at the same time being able to fit batches of images in GPU memory during optimization. An observation is that these 2D approaches discard information along the depth dimension or z-axis and prevents to preserve 3D context, which leads to non-optimal performance. In this work, we evaluate a set of volume uniformizing method in the 3D image domain for the task of tuberculosis prediction. In the first method, called SSS, the slices are sampled from the first, middle, and last position of the entire input volume. A depth-wise stack is then performed over the subsets to attain the desired input volume. To be more representative of the original volume, the second method, ESS, samples by maintaining a spacing factor between the sequence of slices in the input volume. To completely discard the concept of sampling from independent slices, an alternative solution is spline interpolated zoom, which performs the sampling by leveraging the entire volume using spline interpolation. This method retains a substantial level of information from the original 3D volume as opposed to SSS and ESS, which discards a part of the volumetric data. After processing the volumes using the previous uniformizing methods, we train a 3D CNN classifier with two outputs for the binary classification problem. We test each uniformizing method on the MICCAI tuberculosis severity assessment benchmark. CIS yields better performance in both metrics by a margin of 9 and 8% compared to SSS. Since tuberculosis infection can affect any part of the lung, it is not possible to determine which slices are to be discarded without looking at the scans individually. As the annotations are provided at the volume level and not at the slice level, it is crucial to retrieve information from the entire volume. Cross-validation tests also show that spline interpolated zoom not only has a higher mean accuracy than SSS and ESS, but also has a lower standard deviation owing to more reliability. A similar pattern is observed from the RSC curves. This method demonstrates that 3D context plays a crucial role and enables the model to learn effective representations. For all configurations, performance improvements were seen both after pixel normalization and zero centering, with SIZ having the largest gain. We also compare with other methods on the MICCAI tuberculosis prediction task. Spline interpolated zoom, or SIZ, with 3D CNN achieves performance on par with the top ranking methods. It is noteworthy to mention that these methods leverage the clinically relevant metadata in order to significantly improve performance and also develop multi-stage approaches. We further tried increasing the input depth to 128, same as UUIP, but could not fit on a 4 GB memory even with a batch size of 1. Overall, our method performed better than the 3D CNN method by the group UOAP and several of the 2D approaches. Also, among the teams which only used image information, our method achieves the best results. Even though Medgift did not use any metadata, they were the only team that used the lung segmentation masks. We recommend practitioners that analyzing 3D images in a per slice basis is a suboptimal approach that can be improved by 3D context if computational challenges can be overcome. We systematically evaluate different ways of uniformizing CT volumes so that they fit into memory and determine interpolating over the z-axis to be the best. We further validate this approach on the ImageClef benchmark, obtaining 5th position and beat all methods which operate on the CT image alone without patient metadata.